Hello students, hope all of you are well. So today we are going to discuss with the next part of our journey for the complex analysis, that is the zeros and singularities of an analytic function, along with the residue, how to calculate the residues. So again I am telling, if you have not visited the previous video lectures, please go through it, because this is a very important and all those topics are interrelated. So here also, whenever we are going to discuss about the singularities, we have to take the help of the Taylor series and the Lorentz series. So if you have not checked it yet, please check. Now let us start our today's discussion. So first of all, we have to learn the zeros of an analytic function. How to define zeros of a function. So let f of z be an analytic function in an open region D. Okay, now a point z equals to z0 in D is said to be a zero of the function f of z if we can see f of z0 equals to 0. That is, whenever we will substitute z equals to z0 inside f of z, the result is going to be 0 only. Now there are two types of zero we can have based on the order. First of all, the first one is called as the simple zero. So simple zero means that is the zero of order 1. Zero of order 1. So how to get the zero of order 1? That is, if we can see that a function f of z is becoming 0 at z0, but while we do the derivative of the function and putting z equal to z0, it is not becoming 0. So if we can see some criteria has been satisfied like this: f of z0 equals to 0, but f dash of z0 not equals to 0, then it is said to be a simple zero, or simply known as the zero of order 1. And zero of order m, how to define it? It will be the continuation. So here f of z0, f dash of z0, f double dash of z0, so on. If we go to f to the power m minus 1 of z0, all these are going to be 0 only. But whenever we will come to f to the power m of z0, that is not going to be 0. So then z equals to z0 is said to be 0 of order m. Now for your exam purpose, MCQ type of question, say some functions are given to us and we have to identify the zeros of the function and the order of the zero. Okay, so now say we have taken one function f of z equal to z minus z0 whole cube. So we can identify that whenever we will put f of z0, then it is going to be z0 minus z0 whole cube, so the result is going to be 0 only. So by putting z equal to z0, this function will vanish. Therefore z0 is a 0 of this function. Now how to identify the order of this function, order of the 0? So now we have to take the derivative. So f dash of z, this is going to be 3 into z minus z0 whole square. So if we put f dash of z0, then also the result is going to be 0. Now we have to find out f double dash of z. So f double dash of z, this is equals to what? This is equals to 6 times of z minus z0, right? So f double dash of z 0, this is also going to be 0. Now we have to go for triple dash. So f triple dash of z, this is going to be 6, right? So definitely if we put f triple dash of z0, this is not going to be 0. So therefore from here, with this example, what we can conclude, that z equal to z0 is a 0 of order 3, right? Because the triple dash of z0 is not equal to 0. Now let us come to another example, that is f of z equal to z into sine z. So here two functions are being multiplied, right? So if I put z equal to 0, then f of z is going to be 0. Also if I put z equal to n pi, then also f of z is going to be 0, because sine n pi is equals to 0. Sine 0 is obviously 0. So for this z we are having 0. For this sine part, 0 plus n pi, all these values are going to come. So z equal to 0 is a 0, along with z equal to n pi is a 0. Now let us try to identify the order of the zeros. So let me remove this, so it will be helpful for me while writing this part. Okay, so now let us come to the calculation. So suppose we are thinking for z equal to 0, right? Now for z equal to 0, f of z, f dash of z, what will be the value? F dash of z, we have to do the u into v rule of derivative. So suppose we are taking z fixed, then it will come cos z plus sin z will be fixed, so it will come sin z only. So f dash of 0, what will be the value of this? So f dash of 0, it is also going to be 0 only, right? Because 0 into cos 0 and plus sin 0. Now if we do f double dash of z, what will be the value? Then it will come minus z sin z plus cos z and plus cos z. So if we put f double dash of 0 here, now this part is 0, but these two parts are 1 plus 1, so it is 2, not equal to 0. Therefore what we can conclude from here, that is z equal to 0 is a 0 of order what? Of order 2, right? Now if we are going to look out z equal to n pi, similarly we can be able to find out the calculation for z equal to n pi. So let us do the calculation and find out the answer. So let me take another pen. So now suppose f dash of z already we have. So if we put f dash of n pi, what is going to be the result? So it is going to be n pi cos n pi plus sin n pi, right? So sin n pi is equals to 0. So this term will be 0 only. But what is the value of this term? This is not equal to 0. N pi into cos n pi. Cos n pi, if n is an even number, then it will be plus 1. If n is an odd number, so it will be minus 1. So basically this value will become n pi into minus 1 whole to the power n, which is not equal to 0. So if I just put z equal to n pi, then the function is becoming 0, but f dash of n pi is not equal to 0. So we can conclude from here that z equal to n pi is also a 0, is a 0 of fz, but what is the order? Of order 1, of order 1. So z equal to n pi can be think as a simple 0. Okay, now let us come to one important note. Remember that whenever we are talking about zeros of an analytic function, then each and every 0 are basically isolated. Okay, each and every zeros are isolated. What do you mean by isolated? That is, if we make a neighborhood of z equal to z0, so we will be able to see that at least one neighborhood of z equal to z0 is there, exists, where z equal to z0 is the only 0 of the function. Okay, so what is the meaning of neighborhood? Maybe some of the students do not know what is the meaning of neighborhood, so let me explain it. Say we are having z equal to z0 in the complex plane. Say this is the imaginary axis and this is the real axis. Now z equal to z0, around this we have to take a very small radius delta and make a circle around this. So this is called an open disk. So this region which is surrounding z equal to z0 is said to be the neighborhood. Is said to be the neighborhood of z equal to z0. So if we are having a 0 of an analytic function f of z, so we will have at least one neighborhood of z equal to z0 in which z equal to z0 will be the only one, only 0 of the function. Okay, so with that, except that there will be no other 0. So every zeros are going to be isolated only. So for an example, if we just look at for the previous question, then we will be able to see that there are two zeros exist for this function z equal to 0 and z equal to n pi, right? So if we plot the diagram, then what we will have from here, say this is our real axis and imaginary axis, and n equal to 0, z0 equal to 0, this point, and first n pi. So if I put n equal to 1, we are having pi will be little bit apart from, little bit distance from 0. Thereafter 2 pi, similarly here also minus pi, minus 2 pi. So if I make a very small circle surround the point 0, what we can see is there exist any other zeros of this function within this circle? No, because pi and minus pi, these are the closest one to 0, but they are so far from the circle. Because the circle of choice is chosen by me, I can take very small radius and make a circle. So that is known as the neighborhood of the point, right? So within that neighborhood, we don't have any other zeros. So every time all the zeros of the analytic function must be isolated. Now we come to the definition of singularities and the types of singularity. So many times whenever we are dealing with the complex analysis functions, sometimes we will be able to see that for some values of the z, the function may be not defined at all, or the function is not analytic. So those kind of points will bring to the concept of the singularities. So if you just look at this three function, whatever I have written, f of z equals to 1 upon z, fz equal to sin z by z, fz equal to e power 1 by z. So for all these three function, can anyone guess that what will happen whenever we will put z equal to 0 in place of z? So definitely the answer that already came to in your mind, that whenever we put z equal to 0, this 1 upon z, sin z by z, e power 1 upon z, all these functions are going to be undefined at all. So this will bring to the concept of the singularity. Now let us first define what is a singularity. Suppose we are having a function f of z. We are not saying that it is a analytic function or entire function throughout the domain. We are having just a function f of z. Now this function is said to be singular or having a singularity at a point z equals to z0. If we can see that fz is not analytic at the point z equals to z0. This is the first criteria. But in most of the cases, in most of the general books also, we will see this definition has been written just only that f of z is not analytic, but there is not actual the definition of the singularity. Along with satisfying the not analyticity, it should have to satisfy another criteria. What is the criteria? That every neighborhood of z equals to z0 contains at least one point at which the function should be analytic. Okay, that is, we say that one point is a singular point. Definitely at that particular point the function is not analytic, but in that neighborhood, if we make any neighborhood, every neighborhood, okay, whatever choice of delta you are having, suppose I am taking delta equal to 0.1, someone are taking delta equal to 0.01, someone is taking delta equal to 0.000001. Whatever the choice of delta you choose to make the small circle around the point z equal to z0, at each and every case within that circle, at least one point will be there where the function will be analytic. Then the point is said to be a singular point of the function f of z. So for example, you try to understand from this example. Suppose for the function f of z equal to 1 by z. So if I draw the diagram, so at the particular point z equal to 0, this function is not defined. But if I make a very small circle around this point z equal to 0, within this region many points are there, right? Infinite number of points are there. Except the point z equal to 0, we can see the function is completely analytic. There will be no problem at all except the point z equal to 0. Therefore, z equal to 0 will become a singular point for this function. Similar thing happens for f of z equal to sin z upon z and e power 1 by z. But these singularities are also having different types. So let us come to the discussion now for the different types of the singularities. So first we come to the isolated singularity. Let us come to the isolated singularity. So what is the meaning of isolated singularity? That is, suppose for a function f of z, z equal to z0 is said to be an isolated singularity if we can see that it has at least one neighborhood in which the only singularity is z equal to z0. Apart from that, there is no other singularities of f of z exist. Okay, so suppose we can think in this manner that in the whole class only one student is the topper, right? So if it happens like this, that is only one student is the topper of a class, so this topper is become a singularity like this. Okay, so if we can see that in the neighborhood of z equal to z0, we are having only one singularity that is exactly at z equal to z0, except that there is no other singularities, then such kind of singularities are known as the isolated singularity. So for example, let me just give you some example for this. Say f of z I am taking as 1 upon z. F of z I am taking as 1 by z minus 1, z minus 2, like this type of examples. Say I am taking f of z equals to sin z upon z square. So this kind of functions if we are taking, so we can see for the first function at z equals to 0, the function become a singular function, right? And in except z equal to 0, there is no other singularity in the neighborhood of z equals to 0. Okay, now we come to the second function. For this function, if I put z equal to 1 and z equal to 2, the function is become a singular point. But 2 is far from 1. You cannot consider 2 is in the neighborhood of 1. Neighborhood should be considered with a very small choice of delta, very small circle around the point only. For this function also at z equals to 0, we are having the singularity. Other from this point, there is no other singularity exist. Okay, now we come to the second case, that is the non-isolated singularity. For non-isolated singularity, it is said as except z equal to z0, other singularities also exist in the neighborhood. You will not be able to separate the singularities from there. Then that type of singularities are known as the non-isolated singularity. For your example, say I am taking f of z equals to say 1 upon sine of pi by z. Okay, say let us take this example, 1 by sine of pi by z. So now we can see that if I make this sine of pi by z equals to 0, then definitely this function is become undefined, right? So when sine is becoming 0, that is pi by z equals to n pi, right? And if I take this, pi will be cancelled out. So what is the value of z? z is going to be 1 upon n, and n will start from 1 itself. So n equals to plus minus 1, plus minus 2, plus minus 3, and so on, right? Including 0 also, including zeros also. So now, so what we can see, that if I make z equals to 0 for this function, if I put z equals to 0 for this function is also become a singular. Along with that, other singularities also exist as z equal to 1 by n. Now if I draw the diagram, this thing will going to be clear for all of you. So now see, for z equals to 0, I am taking the point here. Now I am taking say 1 upon n. So if I n equals to 1, so this is 1, n equal to minus 1, this equals to minus 1. For 2, it is coming 1 by 2, it is coming minus 1 by 2. For 3, it is coming 1 by 3, it is coming minus 1 by 3. So what we can see, as we enlarge n, all these singularities are coming towards the point 0. So if I make a very small circle surrounding the point z equal to 0 itself, there will be some points where the singularities of this function exist. Okay, so we cannot be able to that is isolate z equal to 0 from that one. That is, all the friends are coming together. You cannot isolate one friend from the group itself. Therefore, these points at z equal to 0 is becoming what type of singularity? It becomes a non-isolated singularity, because close to the point z equal to 0, other singularities also exist. Okay, now these are the main two concepts of the singularity, that is the isolated singularity and non-isolated singularity. Now the next concepts of singularities are coming from the concept of the Lorentz series. For this Lorentz series, already I have made one video lecture based on the Taylor series and Lorentz series. So if you have not checked it yet, you press the I button that you can see in the top above, it is coming. So you can be able to track down that video and you can follow up. So now we come to the Lorentz series idea to generate the singularities. So we know that the Lorentz series of the function f of z about z equal to z0 can be taken in the form of this: n equals to 0 to infinity a n z minus z0 whole to the power n, which consists of the positive powers of z minus z0, and summation n equals to 1 to infinity b n z minus z0 whole to the power minus n, that consists of the negative power of z equals to z0. Now this negative part of z equals to z0, this is called the principal part. Principal part of the function f of z in case of the Lorentz series, right? Now we come to discuss the types of singularities for this case. First type of singularity, it is coming as removable singularity. Removable singularity means what? That from outside it looks like a singularity exists, but actually there is no singularity at all, while we will come to check the whole structure of the function. Now, how to get this type of singularities on the basis of the Lorentz series? That we know that the Lorentz series expansion of f of z equals to this. But if we see that about z equal to z0, the Lorentz series is consist of only the positive power of f of z minus z0. There is no principal part at all at the point z equal to z0. Then such point z equal to z0 is said to be removable singularity for the function f of z. So for removable singularity, the checking procedure is very simple. You have to take just the limit of the function at z equal to z0. So if the limit of the function at z equal to z0 exists finitely, then we say that type of singularity is the removable singularity. So let us take some example for this removable singularity. Say I am taking f of z equals to sine of z divided by z. So this is basically looks like at z equal to 0 this function is going to be singular. But if I just write down the Lorentz series or the Taylor series expansion of sine z, so it will come z minus z cube by 3 factorial plus z to the power 5 by 5 factorial and so on, and divided by z. So z can be simply cancelled down, and the result is going to be 1 minus z square by 3 factorial plus z to the power 4 by 5 factorial and so on. Now if I put z equal to 0, what will happen to this function? This function is simply becoming 1, right? So basically if I take the limit z tends to 0 sine z upon z, this result is becoming 1, which is not equal, that is exist finite number, right? Which is a finite number. So it looks from the outside that z equal to 0 is a kind of singularity, but actually z equal to 0 is not a singularity for this function. The singularity can be removed, so that type of singularity is known as the removable singularity. The next one, that is the most important one, and many things we have to discuss about this singularity, which is known as the pole. We are having a important theorem from here, and the next video lecture is going to I am going to give you the idea how to use the concept of pole to calculate the integrations also using the Cauchy's residue theorem. So now let us come to the discussion. What is the meaning of a pole? Say z equal to z0 is said to be a pole, and it is a pole of order m. If we can see, the Lorentz series expansion of the function can be written as the first part, that is the regular part, will be as it is, summation n equals to 0 to infinity a n z minus z0 whole to the power n, plus the negative power series, it will go up to a finite number of terms up to z minus z0 whole to the power m. If we can see, where b of m must be not equal to 0, then z equal to z0 is said to be a pole of order m. So what is the difference between the removable singularity and a pole? In case for removable singularity, the principal part does not exist. That is, in the Lorentz series expansion, the principal part will go to vanish whenever we put z equal to z0. But in case for pole, whenever we are thinking for z equal to z0, the principal part will contain finite number of terms. Okay, so if we can see in the denominator, we are having z minus z0 whole to the power m. For the last term we are having in the power, that will give us the order of the pole. Now also there are two kinds of pole. That is, the first case is the pole of order 1, that is known as the simple pole, and the pole of order m. So now how to check the pole for a function, just like removable singularity. In case for removable singularity, limit z tends to z0, f of z exists finitely. But in case for pole, limit z tends to z0, z minus z0 whole to the power m multiplied with f of z, this limit is going to exist finitely. But you have to remember, the value of this limit cannot be equals to 0. If it is equals to 0, then it can be a removable singularity. Now to understand it, let us discuss some poles and their orders. For example, I will take this function. I will take this function, say f of z equals to 1 by z minus 1. So here if I see that if I put z equal to 1, then it will become singular. So z equal to 1 is said to be a pole of order 1. Why? Because if I expand that Lorentz series about z equal to 1, this is the only term we are having. 1 by z minus 1, and what is the power of this term? That is equals to 1. So z equal to 1 is going to be pole of order 1. This we can also verify from the limit also. So for limit we have to put m equal to 1 for the previous limit. So we get from here limit z tends to 1, z minus 1 to the power 1 into f of z. What is our f of z? That is 1 by z minus 1. So this value is going to be 1 only. So definitely it is a pole of order 1. Similarly, suppose if I take f of z equals to say 1 by z minus 1 whole cube. So it will become a pole, z equal to 1 become a pole of order 3. So to do this we take limit z tends to 3, z minus 3 whole cube into f of z. So what is our f of z? Z minus 1 whole cube. Sorry, this will be z minus 1 whole cube. So this will going to cancelled out. So the result is 1. That is a finite case. So it is becoming a pole of order 3. One interesting case, suppose if I give, say I am giving here that is z minus sine of z divided by z cube. So this is our function. Then how to get it is a pole or not? Definitely you have understood that z equal to 0 is a pole, right? Now how to identify what will be the order of this pole, or is it a pole itself? The answer is no. Why? Because if I just write down z minus sine z, it will be z minus z cube by 3 factorial plus z to the power 5 by 5 factorial and so on, divided by z cube, right? So z are going to cancelled out, z cube we can divide. So what will be the answer? So from this the answer is going to come, that is plus 1 by 3 factorial plus z square by 5 factorial minus definitely and so on, right? So there is no term in the denominator, that is as a z. So definitely here z equal to 0 is not a pole, So what is this singularity? It is removable singularity. Now the next and the last singularity, that is known as the essential singularity. So if we can see in the Lorentz series expansion, the principal part contains infinitely many terms, then that type of singularity is known as the essential singularity. Okay, so we can just break down or make a summary. So if we are having Lorentz series, if only the principal part is not there at all at z equal to z0, then z equal to z0 is said to be the removable singularity. If the principal part contain finite number of terms, then it will be a pole of order m, if we are having highest power as m. Now for essential singularity, if we can see the principal part, that is the negative power of z in the expansion, contains infinite number of terms, then is such type of singularity is known as the essential singularity. So let us take an example to understand this essential singularity. Say I am taking e power 1 upon z. So if I take e power 1 upon z, then what we can write down about this? The series expansion of e power 1 upon z is 1 plus 1 by z plus 1 by z whole square divided by 2 factorial 1 by z whole square divided by 2 factorial plus 1 by z whole cube divided by 3 factorial and so on, right? So here all the powers of z are coming in negative only, z to the power minus 1, z to the power minus 2 by 2 factorial, z to the power minus 3 by 3 factorial, and so on. So at z equal to 0, this function not only undefined, but it is having the essential singularity. Okay, what type of singularity it is? It is essential singularity, because at the point z equal to 0, the power of z is becoming in the negative power. Negative power is not going to end here. Principal part will contain infinite number of points. Now we are having just two statements of the two theorems. Let us try to understand it, because it will be helpful for discussion. So next is theorem 1. It says that suppose we are having an analytic function in an open region D, and we define another function phi of z equals to 1 upon f of z, right? If we can see that f of z is not equals to 0, and say f of z has a 0 of order m, f of z is having a 0 of order m. Since phi of z equals to 1 by f of z, so the zeros of f will become the pole of phi, and the order is not also going to change. The order will be m only. So if we can write down one analytic function like this, phi of z equal to 1 by f of z, so the zeros of f of z will become the poles of the function phi, and the order of the zero will be the same as the order of the pole. Next theorem says that the limit point of zeros is always isolated essential singularity. Okay, limit point of the poles are always isolated essential singularity. So what is the, how to make the find out the singularities for this one? That is, if I put that is 1 by z equals to n pi, limit point of zeros, sorry, here we need the zeros only, right? So if we want to make this equals to 0, then I have to put sine of n pi, that is equals to sine of 1 by 1 minus z, right? Therefore 1 by 1 minus z equals to n pi only. So what is the value of z here? So z will become 1 minus 1 by n pi, and n will start from, say, plus minus 1, plus minus 2, and so on, right? Eventually, if I take n tends to infinity, what will happen? It will become z equal to 1, because n tends to infinity, 1 upon infinity is going to be 0, so the value of z is going to be 1. Okay, so the limit points, each and every point here are the zeros, because if I put every point as z equals to 1 minus 1 by n pi form, the function will become to be 0. But the limit point of these all zeros set of all the points here is equals to 1, which is nothing but isolated essential singularity. Next one, limit point of poles is also be singularity. What type of singularity? It will be non-isolated essential singularity. To understand this, I have taken one example, sec of 1 by z. So sec of 1 by z means that is equals to 1 upon cos of 1 by z. Now if I make the denominator equals to 0, that is cos of 1 by z equals to 0, then what I will get? The value of 1 by z. So 1 by z is going to be 2n pi plus minus pi by 2. 2n pi plus minus pi by 2. So what is the value of z? So z is going to be 2n plus minus 1 by 2 into pi, where n will start from 0, plus minus 1, plus minus 2, etc, etc. So each and every point here, the value of z is nothing but the poles. Each and every values are poles here. But if I take limit n tends to infinity of all these points of the set, this is a set of all points, so if I take the limiting point of this set, what will be the limiting point of this set? The limiting point of this set will become 0, okay, which is a non-isolated essential singularity. Now we come to the last point of our discussion, that is the residue. So what is the residue definition? If we just draw the Laurent series expansion, then we see the first term in the negative part, that is the principal part, it will start with first coefficient b1 by z minus z0, right now. For your understanding, I am just writing. So the Laurent series expansion of f of z equals to summation n equals to 0 to infinity a n z minus z0 whole to the power n plus summation n equals to 1 to infinity b n z minus z0 whole to the power minus n. So this, it will start with b1 upon z minus z0 plus b2 upon z minus z0 whole square, and so on. So this coefficient, that is the coefficient of 1 upon z minus z0 whole inverse, this v1 is called the residue. This is the actual definition of residue. So whenever we will make the Laurent series expansion, in the principal part, the coefficient of 1 upon z minus z0 is known as the residue. And what is the value of residue we can calculate? In the Laurent series, I have told you how to calculate this bn. This is 1 by 2 pi I integration over c f of z minus z0 to the power n minus n plus 1 dz. Since we are having b1 here, so in place of n, if I put 1, then z minus z0 whole to the power 0 it will come, so it will become 1 only. So from here we can see the value of b1 is 1 upon 2 pi I integration over c f of z dz. Now based on the types of pole, we are having the two formulas which are the most important formulas for calculating the residue. If we are having a simple pole, then the residue can be calculated using this formula, that is limit z tends to z0, z minus z0 into f of z. And if it is a pole of order m, apart from pole of order 1, if it is a pole of order 2, order 3, order 4, etc., then we have to find out the residue of z equals to z0 using this formula, 1 by m minus 1 factorial limit z tends to z0 d to the power m minus 1 dz to the power m minus 1 z minus z0 whole to the power m into f of z. So based on these two formulas, we are going to calculate the residues of an function, an analytic function. So with this, today's topic, I am going to close it. So if you understand this topic, please subscribe the channel and share with all of your friends so that everyone can get the information. Thank you all.